Welcome to the seminar today. We're basically going to talk about demystifying statistical process control, as the title says. My name is Andreas Klieber, and I've worked in the food industry over the last 30 odd years, I would say. Unfortunately, that ages me a little bit, but just to give you some sort of idea that this is a topic that comes and goes at different times. And last time this got a really big push was when SQF came out and says that every business that's SQF certified needs to undertake statistical process control. I think that caused quite a bit of anxiety in people, and SQF has taken out the word statistical out of their standard. But if you talk to the people that are actually writing the standards and the experts within it, they clearly still expect that the businesses that they certify have process controls in place and make sure that the food is produced safely, but also with good quality. Now, there's a very good reason why not just SQF, but also your clients want you to have processes under control. And part of that is that if the processes are not under control, you're going to have a lot of waste. The costs go up through that, and therefore your customers really want to have a consistent quality product that doesn't waste money, so they can basically give good value to their consumers in the long run. And so there's a lot of emphasis on that because it's going to be a consistent product produced consistently day in, day out. And there's some companies out there that are absolute masters at that. And I would think of, for example, McDonald's, where it doesn't matter where you go in the world, the beef patty is going to be looking the same, exactly the same dimensions, doesn't matter which burger you purchase. And so they're very much on top of that. And that's because it's a quality statement, but it's also a cost control method. So just briefly, a little bit about Quality Associates. We do deal with all the retail majors here in Australia. We also work with extensive range of other industries, from FMCG, everything from meat, seafood, produce, distribution, and so on. And so we've got a pretty wide view of the industry. And the services that we provide are training, consulting, but also supply chain audits and inspections, labeling reviews. We work with food safety culture and on-site support. As far as training is concerned, we have in-house training and public courses, but we also have an online training portal where you then can do some of the key topics, such as the HACCP refresher. We have a food labeling course where we actually discuss the new updates for the PL requirements in the Food Standards Code, allergen management, HACCP and VASCP, and so on. And for early career professionals, we basically have a group of different courses we bundle together, which is our QA Accelerator program, where you can do quite a few different subjects at a much discounted price. So principles of HACCP, practical food micro, allergen management and vital, and so on. But enough about us as a business. What we're really here to do is about talking about statistical process control. And, you know, most of us, when we were thinking about the word statistics, we think back at our uni days and all the difficult type of studies we had to take, analysis of variance and a whole range of these sort of things that in reality we might use in research, but isn't going to have much of a place within a food manufacturing environment. So I think what we need to do is really step back a little bit if we want to understand what we're actually talking about here. And so statistics comes back to its simplest form, really. And that's making sure that we're drawing the right conclusions from numbers. So that's measurements, for example. So we'll talk about some of those measurements in a little bit, but basically what this is all about is making sure we can make some conclusions whether the processes are actually in control. And so the second component of SPC is then the process. And the process is combined out of a whole range of different parts. It's operators and machines, it's raw materials, it's how we're sampling things, what the environment is. So for example, if your factory environment becomes hotter during the day, what is that impact then going to be on the processes that are happening within that environment? So all of those have an impact, therefore, on how that process will be conducted and how consistent that's going to be. And then control just simply means we're going to keep the process within defined boundaries. So we don't want to step outside of those. So that might be, for example, when we're cooking something, we might have an upper temperature and a lower temperature that we need to sit below. And then when we're looking at statistical process control, we then are going to have some tools to see whether we're consistently under control as far as that's concerned. And so basically by keeping things under control, it helps us to ensure that we comply with critical limits. And that's quite important really for our HACCP systems to work effectively. And it's going to use real-time analytical data to look at changes and see whether a problem is going to happen in the future. So we can actually adjust the conditions and make sure we don't have a problem. So there are quite a few benefits to statistical process control. It helps us to operate efficiently. It makes sure that we produce more product within specification, therefore going to have less waste. It emphasizes early detection and preventing problems rather than waiting for them to occur. And it helps us to reduce variations in the process. So we can measure changes over time, and that might give us an idea. For example, as equipment wears out, we might need to replace something because we're seeing that variability increase, for example. And so the output out of all these improvements then are safer, higher quality food, decreases in production cost, increases in efficiencies, and compliance with regulations. And that's really why the standards and the retailers and other customers that you're working with are really looking for you to have control over your processes. All right, so if we want to make conclusions about measurements, we need to first start in collecting data. And so that's the very first part of the whole equation if we're going to set up our system. And so that could be process measurements, readout from various machines or instruments. So it could be temperature reading, it could be a pump gauge that shows your pressure, it could be pH reading. So there's a whole range of different things. It could be even things like sensory attributes. Weight, for example, could be one that you could also look at and start tracking and trending and seeing how well you're controlling that. And clearly, if you don't control weight very well, you might have a lot of giveaway. And so that has an economic impact as well. It might be safety attributes, so you can track microbial counts, for example. And so that data then is recorded, and we have a number of different tools that we can use that are called control charts. And those control charts can then help us see how we're going over time and whether our processes are going to be under control. So I'll just park control charts for a little bit. We'll come back later to them to explain a little bit more how they're created and what that might mean as far as the operations are concerned. So basically, the data that we collect has to then be charted, as I said, and we need to make sure that we choose the right charts. And as I said, we'll talk about that. But the first thing we really need to understand is that there are going to be variations in any process that you go through. And there are really two different types of variation. The first one is called common cause variation. And that's basically things you expect to be variable. So slight temperature fluctuations because then process environment changes in temperature. It could be the raw material has some variability. So you're always going to see some variability within any process. And even if you're focused on reducing that variability, you're going to get to a point where it becomes too expensive to remove further variation. So as long as what that target is showing you there is basically these 5 dots, they sit in the center of where you need to be, so you're within specification. As long as that variation is that small, It's basically something you're going to live with. And so what we then need to do with statistical process control is to find that special cause variation. That is when something goes wrong, whether we had a failure, the process has changed, something is broken, operator hasn't done the right setup. There could be a whole range of reasons why we're getting to that special cause variation. And so really that's what we're trying to detect and try to deal with. And so basically we're using the statistical tools to look at our performance, see whether we're going to have variations that are significant and may produce substandard products. So that's really what we're trying to find out with statistical process control. So when is a process under control? And so I've just gone back to the footy field just to make that a bit easier to visualize. But basically, a process is under control when there's no special causes that have been identified and where we only have random variation. So it's not going to be something that's going to impact massively on the process. And so if you look at the footy field and you basically kick in the middle, you get 6 points, you kick on either side, you get 1 point, you go out on the full on either side, you get no points. And so under normal conditions, a team might kick generally through the middle and a few on the left and a few on the right, and that gives you a pretty good score. Now, if you now start seeing anything more than this sort of random variation that you're going to get, so in the second line there, where people basically spray the ball all over the place, it's not going to go where it's supposed to be, you're going to get a very low score. And that's the same that's going to happen with any system. If you can't get that into the middle, operating consistently, you're not going to do well. You're going to have lots of waste. You're going to have lots of downtime and issues because you need to keep fixing the system as it's running. And so that's really what we're trying to achieve. So we need to then look at the data distribution, like on the footy field, we want lots of data close in and a little bit further out. But basically what we want to do is actually measure that distribution, because that gives us valuable information of how consistently we're actually operating. And so if we plot that on a graph, what we want to see is a normal distribution. And the normal distribution is just basically bell curve, and I'll show you that in the next slide. But that's basically what we need to have for the data to be analyzable as far as statistical process control is concerned. Now, luckily for us, most systems, whether they're measurements we do on people or equipment or anything else, generally tends to follow the normal distribution. So that's pretty straightforward in most cases. If the data is not, and there's a number of different reasons why data might be skewed, or you get 2 different peaks, or a whole range of different things, you need to then correct the data. Now, I won't go through that today because that gets a little bit more complicated, but basically just let's keep in mind we want a normal distribution. So that's what a normal distribution looks like, this typical bell curve, and I'm sure you've seen that plenty of times in your life. So basically the characteristics of a normal distribution are that the mean, median, and mode are all the same. So mean is just the average, median means 50% of points lie above and 50% of points lie below, and mode is just simply the count of what number occurs the most, which is then going to be at the center. So that's what basically characterizes a normal distribution. And then on the bottom there, you can see the standard deviation shown. So 1, 2, and 3 standard deviations going to the right, -1, -2, -3 standard deviations to the left. And so the characteristic of that is when you get to 3 plus or minus 3 standard deviations, there are very few points outside of that range. It's only 0.3%. So 99.7% of points, data points, lie between those 2 red lines. And so that's something that we can use for our control charting, because in control charting, we're going to see whether our data lies between those two lines, the plus or minus 3 standard deviations. And you can see from that, it's very unlikely that we should see any data outside that range. And clearly, if we do, we think we have a problem. So we then need to investigate. And that's really what the control charts help us do. There's a few more things that we're going to learn from how we're charting it and the information, but keep just in mind that basically when we're looking at plus minus 3 standard deviation, chances are our points should be in between those two limits. And so just to show you just a little bit more standard deviation, if you have a small standard deviation, you have a very narrow range of data. If you have a large standard deviation, you're clearly going to have a wide range. We do like using standard deviations if we have enough samples, because it's a better measure than a range in itself. And so we tend to, when we can, use standard deviations rather than just a range from plus, minus whatever that point might be. So thinking about calculating then a standard deviation, here's the formula. Luckily, Excel can do it all for us. But basically, the standard deviation is basically the data point minus the average squared. You sum up all of those squares divided by the number of observations and take the square root. So a little bit difficult to remember in detail. On the right-hand side there, I've just shown the calculation in Excel. You basically have 10 data points. You have 10 values to go with that. And on the right-hand side, the formula for an average, which is 1.52, and the standard deviation for the population, which is 0.25. You can also do a standard deviation for sample. If you're only dealing with a small sample size, the value is slightly different. So you just need to understand which one you're going to choose. But basically, if you can put your data into Excel, it's very easy to calculate your standard deviations. Okay, that then gets us into control charting. So we've now measured data, we looked at the distribution. If it's normal, we can now start thinking of how can we actually then prepare that data so we can draw some conclusions. And so that's where control charting comes in. So control charting is basically monitoring data over time. It is a regular process. It helps us to see whether the process is drifting out of control and whether we need to do something to adjust it. And therefore, we can be proactive before we're going to see a specific problem. In control charting, generally, the control chart is going to have 3 lines drawn within that. And so the first one is a center line. So that's the mean of all of the data. So we can see whether we're operating close to that. And then we're going to have an upper control limit, which is basically plus 3 standard deviations from that center line. And we're going to have a lower control limit, which is basically 3 standard deviations below the center line where we want to operate. And basically within that range, we're going to have 99.7% of all of our data points if we're operating consistently within those limits. And so we can then look at the data points over time and see how we're actually trending over time. So just to show you what that then might look like, on the right-hand side there, for 11 data points over time, we've got a measurement that goes between 0 and 18. Doesn't matter what that is. You can plot really just virtually anything with numbers on that. And basically, you're going to see the mean, and you want to operate close to that generally. And you have that upper and the lower control limit. And very clearly in this case, where our data point 8 is, we can see we're way out of the upper control limits. And so something has gone drastically wrong, and we need to investigate that and make sure that we can actually manage that. And so that's some of the information we can get out of that. Clearly, you're not always going to see such drastic deviations. And I'll talk a little bit more about how else you might draw conclusions out of this data, but clearly that's just an extreme example of where things are really going wrong. Now, you need to also keep recalculating the mean and the upper and lower control limits, because whatever data set you have, as that set gets bigger, the operating mean might shift over time. And so you need to keep recalculating those limits to reflect the current process behavior. So it's not something that's static, but it's something that will keep changing. And so that's something you therefore need to keep reevaluating as well. So let's have a look at a couple of examples. And the first one is a very simple one. It's an attribute control chart. It's very easy to control. It's a good starting point to just get your head around how this might work. And so for this example, we're looking at a C chart, and C just stands for count. So basically, we're going to have a control chart that looks at how many defects or non-conformities we're finding in specific batches. So let's just step through that example. So the data on the left, we've got 8 batches. So that's basically the number K is 8. We've got non-conformances for each of those batches going from 2 to 15. And so each non-conformance is labeled as CI. So the CI for batch 1 is 2, for batch 2 it's 4, and so on. And so if we're then summing up, so that's the symbol, the sigma there, if we take the sum of all of those non-conformances, that's basically 60. So now we've got the information we need to calculate the center line and the upper and the lower control limits. And the center line is just basically the sum of all of those non-conformances, which is 60, divided by the number of batches, which is 8. And we get the value for the midpoint of our chart at 7.5. So that's the average of all of the non-conformances across those 8 batches. The upper control limit is just simply that mean plus 3 times the root of that mean. And we plug in the data, we get 15.6. And for the lower control limit, it's basically the mean of all of those non-conformances minus 3 times the root of that average non-conformance. That gives us a value of minus 0.7, but since we can't have negative non-conformances, that automatically goes to 0. And so if we think then center line 7.5, upper control limit 15.6, and the lower control limit at 0, this is what that chart looks like. And for each of those 8 batches, I've also plotted in the actual data. So batch 1, we had 2 non-conformances, batch 2, 4, and so on. And while the data intuitively would have shown you that we're starting to trend up, having this view makes it very easy to see we're really going on the road to nowhere. We're getting more and more problems, and we need to get those under control again at some time. And so while this is a very obvious example, because I just want to highlight how we use this, in reality, you're going to have more subtle changes. But nevertheless, you can get information out of that that can be quite useful. So that's a simple C chart. If you do complaints per million units, they're equivalent charts for that as well. So then we're looking at P chart for percentage defects and things like that. So there's a few different ways in which you can deal with attributes. When it comes to data like temperature, time, pH, water activity, whatever measurement you want to take, we then start looking at sets of charts, and they're always in groups of 2. And the X chart is basically the mean. So basically, is the average trending over time in the way that we want or not? And there's going to be generally an S chart, which stands basically for standard deviations. And the S chart basically tells us whether our variability for each batch or each measurement set is becoming excessive or not. And so you can imagine that you don't want a lot of variability. Equally, you also want your mean to be as close to where you want to sit as well. And so there are 2 factors that we're really looking at here. Generally, you will plot the S chart first. If the S chart looks under control, you then look at the X chart. So as long as your variability is under control, you then want to see how you're actually going in relation to the actual mean. And so those charts together, you can also, instead of the standard deviation, do that with an R chart, which is basically a range. But if you have sufficient measurements, as I said, standard deviations are better to use because they're better to draw conclusions about data distribution from. But again, each of those charts, whether it's the X chart or the S chart, you're going to have that process average or the standard deviation average and an upper and a lower control limit. And this is just basically what I've shown in here, where you see the midline and the red lines are basically indicating your limits. And if you just look at both of those charts, you would say, okay, looks like we're pretty much under control. We're staying close to the center line. We're not getting close to the upper and lower limits. Maybe if you look at the S chart, we had one batch where we had a bit more variability, and that was number 19, but that corrected, and over time, we didn't really see a significant issue. And so that gives you then some confidence that your processes are under control. So just briefly then, how you might go about calculating those X and the S charts. And so there are a number of steps that you would do. And the first one would be to determine the sampling plan. And clearly, the more samples and measurements you take, the better statistical valid data you're going to get. You then need to collect your samples in time sequence. So at point 1, you might have 3 samples. At point 2, you take another 3 samples, do your measurements, and that then feeds into that system. For standard deviations, you probably want to be around 10. That gives you a much better idea. If you're down at 3, you're probably looking at a range. So now that you have those samples, you can start calculating the average for each of those sample types. So each one of those 3 or 10 measurements will basically have an average, and you calculate that. You also calculate the standard deviation for each one of those sample sets. So for sample set 1, sample set 2, you're going to have a mean and a standard deviation. And then to calculate the center line, you're basically going to take the average of all of the means. So you're basically doing the first mean, second mean, third mean, and so on, and you average those out. And that's going to be your center line of the X control chart. And then you do the same thing for the standard deviation. You do the mean of all of the standard deviations that you've calculated, and that's the center line for the S control chart. So relatively easy just to do the mean and the mean of the means and the standard deviation and the mean of the standard deviations to calculate the center lines. And then the next thing you calculate is basically the control limits. So UCL upper control limit, LCL lower control limit. And in this one, we're basically using the average of the means and the average of the standard deviations to calculate those figures depending on the charts. And on top of that, there's some values in there, B4, B3, and A3, and they're basically called factors. And those are in control charts where you basically look up those factors that have been published. And so you basically look up those values. So you don't need to calculate anything. You basically go straight to the tables and plug that into your equations. So it's basically 3 steps. We do the average and the standard deviation for each point. We then do the average and standard deviation across all points. And then we plug in that data to calculate those control limits. And from there, you can then basically plot. For the upper control limits for the S chart and the lower control limits, it's just simply a factor times the mean of all of the standard deviations. And for the X chart, it's basically the average of the means plus a factor or minus a factor times the average of standard deviations. So as long as you go systematically through calculating those points, it's actually relatively easy, therefore, to calculate the midline and the upper and the lower control limits. And I'll show you the one of the factor charts here. And so there's a whole range of them, depending if you have different charts, they're going to be basically different factors. So you need to select the right factor chart. But basically, if we want to know A3, B3, and B4 for our X and S chart, we basically have to know the sample size for each point. Say, for example, we have a sample size of 10, and if we then track across, the factor A3 is 0.975. The lower range factor, basically B3, is 0.284, and the upper range factor B4 is 1.716. And so that's basically what we look up and plug into those equations. So it's just basically taking the data, doing some very simple averaging standard deviations, and then looking up those factors. So that's basically all we need to do to create them, and then we plot the data into that chart. Also, just keeping in mind, as I said, that the longer your data gathering goes on, those upper and lower limits, as well as the center line, might drift over time. So you will need to recalculate those over time. And so then once you've plotted your data, you then need to start thinking how you interpret them. And I've just given you two examples in the next couple of slides of how that works. There are lots of other things to think about, looking at other ways where things are not going as intended. I'll just show you two examples. And clearly, the first one here, trends, you can see you're going from a relatively high value, and each time you measure, the value just becomes lower and lower, and we're clearly heading towards the lower control limits. So then we have to start thinking, if that trend exists, what is actually the potential cause? And so that could be because a piece of equipment is deteriorating or process isn't quite working as it should. Somebody might be interpreting data incorrectly and letting the measurements drift over time and not readjusting things, or could be just simply an unstable operating environment. So basically, if you're operating normally in a cold environment and that doesn't quite work for some reason, all of a sudden you're going to have warmer temperatures, then that can impact on equipment. So you need to start thinking, what are the underlying causes then when we're seeing those sort of trends? But by the time you get to this stage, you do want to do something proactively and stop from going below that lower control limit. Another example there are runs. And so basically, where for some unknown reason, all of a sudden, all the data points fall on one side or the other of the mean. And so those 5 data points I've highlighted there, they're basically all below the mean, when all the other data points are really falling randomly around that mean itself. And so again, we need to start thinking, what are some of those potential causes? So has the process mean shifted just for some time, and what might be the reason for that? So it could be that equipment performance changed, or an operator came in and stepped in and they're running the equipment differently to what everybody else does, and all of a sudden the whole setting has changed and the mean has actually drifted. Or you could have had a batch of raw materials that basically impacted on the process that's atypical to what you normally process, and that could therefore result in the mean shifting from that point of view. So you don't just do control charts just to see whether points fall outside that, but you're trying to get as much information out of it so you can actually proactively manage your processes. Now, I need to give you one very big warning note, and that is, you cannot rely on this aggregated data to know whether your critical limits or, in fact, your quality limits were under control. All that control charts do is show you aggregated data. It's means and standard deviations. It doesn't show you individual data points. So it's all about statistical control of your processes. But when it comes to your CCPs or QCPs, individual data points matter. In all of that aggregated data, it could be all looking fine once you've done average, but you could have had one point that didn't meet a critical limit, in which case you have a significant food safety risk. And so you can't just rely on statistical process control saying everything is under control, our critical limits aren't in breach, because that data doesn't give you that type of information. So when it comes to CCPs or QCPs, you still need to consider individual data points, not just the aggregated averages and standard deviations. So I think that's quite an important one to remember when we're operating, otherwise we can also get into trouble. Now, once we have things under statistical control, we can also start looking at process capability. And process capability is all about how well can we produce and be within specification limits. So are systems actually capable to deliver what we want them to deliver? I won't spend a lot of time on that. I just want to touch on it just to give you a bit of a flavor for that. But basically, this is all about measuring the relationship between your process control limits and whether they're going to fall within specification limits. And specification limits could be as simple as our client wants, for example, always a height of a cake that's 5 millimeters or whatever it might be, and we have a tolerance of ±1, can we actually deliver that? And so that's what you're trying to find out with process capability. And you can use that to look at your current operations, and you can then look at whether, say, if you wanted to get new equipment, whether the capability is actually going to improve significantly. So it's basically trying to meet specification and customer requirements. To do this, though, you have to be under statistical control. So you need to go through the control charting first and see that that's actually operating properly. And then basically you're trying to minimize your special and common cause variations. So as I said before, your common cause variation is just the normal variability you see in the process. And you try and minimize that, but as I say, there's a point below which it becomes uneconomical to basically keep reducing that. And special cause variations, well, you don't want to have things going wrong, and that's why you're looking at your statistical process control to see if processes are under control. And then if you're looking at process capability, there are two indices to calculate, a CP and a CPK. That's basically all about process capability. If we're looking at our target charts here again, just to give you an example, if you have a high CP and a high CPK, that means that data points are close together and you're hitting the bullseye of your target. So basically, it's easy to achieve the specifications that you were set out to meet. On the left-hand side there, if the CPK, for example, becomes too low, that we calculate, then we're going to start seeing the whole data set drift further out on that range. And basically, we're going to potentially have lots of product that's not going to be within specification. And so that's where CP and CPK can help us actually see how well our processes are designed and how well we can actually deliver against specification without having a huge amount of waste. So if you're now looking at getting started and want to set up your statistical process control within your business, there are a few hints of do's and don'ts that I just want to go through. As with anything, practice first. Start with a small area and see how it goes. As you become more confident in doing that, it just becomes easier. Anybody that works with this will need to be trained. So a lot of that data is going to be gathered by line operators. And so they need to actually understand how to chart, what calculations they have to do, or if you have a computer that does a lot of the calculations for them. But basically, they need to understand what they're doing, but they also need to know what to look for. So trends and runs and those sort of things, and what corrective actions they need to do. It's often easier if you start on paper rather than setting up complicated systems, because you actually practice and learn how to do it, and that helps with understanding. And then you want to set some goals around that and making sure that it helps you with improving quality, for example. So you don't just want to throw charts at everything, but you want to start looking at where do we have particular problems and how can this tool actually help us to improve. The don'ts, so don't just start everywhere at once. I think you're going to stretch yourself. It's going to be hard training everybody relevant, and it's just going to create a bit of confusion. You need to build a bit of confidence in the system, see actually getting some results and see how you're actually making a change. And that may not be drastic or immediate. It might take a little while until everybody gets familiar and gets more proactive in dealing with some of those situations. It's not just a tool for the manufacturing floor. There are lots of other opportunities to look at that. And the other thing then is to not sort of go out there and saying, oh, you know, we've just been asked by SQF to do this, you know, next month there'll be something else. So it doesn't create momentum within the business to actually start implementing something like statistical process control. All right, so that's all the time we have pretty much for today. I just wanted to flag we do run courses in statistical process control and also an average quantity system. We have a public course coming up on the 26th of May if you're really interested in finding out some more. But otherwise, I'm just here to answer your questions now and see if you had any other things that you wanted to know from the session today. Thank you.
Thanks, Andreas. That was fabulous. A lot of information packed into a very short time. So really appreciate you taking the time to take us on that journey. I think statistical process control has always scared me. And my first memory of it was actually doing a statistical process course when I was very early on in my career, and it was taught by a guy who was actually the poker champion of Australia.
Okay.
So he did get people's interest.
Yes,
I think everybody came along hoping that they were going to learn some techniques to win at poker.
Okay.
Look, so we do have a few questions.
Sure.
So fabulous, thanks everyone for that. So the first one is, in a specific batch of production, how do we know how many samples to take?
Okay, so I guess that comes down to lots of different things. How long your run is. So you need to make some sort of call on what a sensible measurement size is. If you want to do S charts, it's a minimum of 10 generally to have sound data. If it's less than that, you're going to use R charts generally. So there's some of the things. It's also a bit of the history. If your data isn't all that variable, you probably don't need to measure as often or as many duplicate samples. So that might be one consideration there. Also, to some degree, if that's destructive sampling and the cost is really high, that might be something else that impacts on it. So it's going to be case by case, looking at your own operations and making a judgment of how much information you need to effectively measure that.
Thanks, Andreas. The next question is, how can a small company implement statistical process control when batch sizes are small and sample sizes are small? For example, a bakery making 300 loaves a day. Yep.
Okay. So you might just then treat a batch as 1 day's production if you only have 300. And it depends. If it's non-destructive testing, you might take, say, 5 loaves and measure their height, for example, if that's one of the key quality parameters that you're looking for. You can even do it for weight and start looking at how variable it is. Can we get weight under control so that the pack or the giveaway isn't excessive, but equally we're not going to go too low so that we're not going to underpack. So that depends on the measure and what you want to really improve and for what purpose. So there's no fixed rule. It really looks at what are your key issues. And if weight is a key issue, fine. If the height of the loaf is a problem, then that's another way of thinking about it. And so it's really finding something where this is going to be most relevant and start with that, really. Sorry, Fiona, you're on mute.
Sorry, I'm on mute, yeah. I think what I also took out of that is really being able to understand your process as well. You know, really understanding what you want out of it. Okay, so the next question we've got, great presentation. So any applications where you are completing this in real time, or will it always be completed after the fact with aggregated data?
So I guess if you do look at quality control samples that you take offline, that's not going to be real-time data, but this is used by manufacturers extensively on the factory line. So where basically you might have to adjust for temperature, for example, that's slightly fluctuating over time, and that's a CCP, and somebody stands there and basically manages that. So in that case, you will have plotting in real time, recalculation might happen, say, on a daily basis. And so basically they'll have the control charts, and as they start seeing trends or other issues, they can then start acting on those. And that's why it's important to then tell the operators what you expect them to do. What you don't want them to do is tweaking where they just adjust a bit this way and now it's turning the other way, and then they tweak it that way, and the fluctuations just become bigger and bigger until it's out of control. So, so while it can be used in real time, people need to understand how to make use of it without creating more problems.
Good point. Last question. So what are the guidelines when to take action before limits are exceeded?
Again, it comes down to a number of factors. Clearly, if you're drifting to exceed quite significantly and it's a CCP, you want to then basically have somebody assess what that means. So you might have to stop the line, you might have to get the quality manager involved and make a call on, well, you know, what that means. If it is something else rather than a food safety issue, then it comes down to whether you're still going to achieve the right quality of the product. Can you adjust and while you're operating and still achieve a reasonable quality, or is the product going to be burnt and not saleable, and therefore you might actually need something more drastic, which might mean stopping the line, cleaning out whatever caused the issue, resetting and restarting again. So there's no hard and fast rule. It depends on your process and the specific thing that you're measuring and what the significance is as you're starting to deviate.
Great, thanks, Andreas. So we don't have any more questions. Oh, hang on, we do. So where can you find the right factor chart for your process and measurement?
Okay, factor charts, you jump on Google, there are lots of them out there. So for example, if you know that you're doing an X and an S chart, you know the factors. So basically, you can search for factor charts that then look at that B and A factors. And so you basically see if they're the right charts or not. They're probably also published in books, but basically it's quite easy to look up. And then it's basically just knowing which charts you're constructing and the sample number. And that's basically all you need. Great,
thank you. All right, well, that's the last question. So we might just flick back. Sorry, I'll just go back to, I just really like to thank Andreas. Fabulous presentation.